Hi everybody, Mr. Sharkey back with another exciting chemistry video. Wow. Um, Today we are going to look at the energy change in the Icy Hot Labs page, which is in our Blue Notes packet for Unit 3. And what we've done here is we've taken the Icy Hot Lab and we're actually going to go ahead and do some calculations with it. So up here at the top, I've got our 4 different constants that we just went over in the constants video. If you want to go back and look at that, I'm sure your teacher shared it with you. But what we're going to do is we're going to look at the heating curve that we created in this lab, and we're going to go ahead and actually calculate the amount of energy that our water absorbed. So reading the question here, or our initial prompt, it says, assume that during the lab, 100.0 grams of ice was placed on a hot plate and heated until it completely boiled away. Calculate the energy required to cause each change to the ice that would be observed during the experiment. So we're going to break this down into 3 different steps for each of the phases, or each of the changes our water underwent. And then we're going to go ahead and total those up by adding them together to figure out the total amount of energy. So as I look here, I've got my 4 different constants. So the heat of fusion, which we'll use for melting and freezing. The heat of vaporization, which we'll use for vaporizing and condensing. And then we've got the specific heat capacity for solid water and the specific heat capacity for liquid water. Again, to go back and see when we use each of those, you can watch the video beforehand. What I want to do to start us off is I just want to go ahead and draw a full heating curve for what we would expect to happen during the lab. So in our prompt, our beforehand, the water is starting at 0 degrees Celsius, and we get all the way up into that boiling point. So we're just going to assume that we boil all of the water. So here, we're starting at 0 degrees Celsius. The very first thing that we're going to do, if we have ice right at the melting point, its temperature can't actually go up yet because 0 degrees Celsius is the hottest that ice can get. So we're going to start off with a phase change, which we've talked about is represented by one of these horizontal regions on our heating curve. Then, after that phase change, once all of our solid water has become liquid water, the temperature can start increasing again until we hit that boiling point, which is 100 degrees Celsius, and then we're going to have another plateau or another flat region. So our heating curve overall is going to have this shape. And what I'm going to do is I'm just going to go ahead and copy down roughly that same shape in each of these portions of my graphs. And rather than just drawing one specific section, I like to have the whole heating curve in front of me, and then we're going to highlight the relevant areas. So we're starting off with this first section of the graph. I'm going to go ahead and highlight what we're going to use. So I'm trying to be consistent with the previous video. I think we used blue for this section. So in this first part of the graph, which is the bit that I've highlighted in blue, the first thing we need to do is figure out what's changing about the water. If I look at temperature, this blue region starts at 0 degrees Celsius, and then it also ends at 0 degrees Celsius. So the temperature is not changing. What that does help me identify is that the state is changing here. If you're familiar with these heating curves, hopefully you've recognized that this is the melting portion of our heating curve. And what's nice about that is that if we can recognize that this is melting, we can recognize, I don't know why that highlighted both. We can recognize that means we should be using our heat of fusion. So when it comes to the constant, we're going to use heat of fusion, which says that it takes 334 joules of energy to melt exactly 1 gram of water. So when we get to our calculation, we're always going to start off with that constant, and I would get in the habit of phrasing it in your head the way that I'm saying it out loud, because I think that helps us make sense of the information we need to put on the other side. When I read this constant, I think of it as saying it takes 334 joules of energy to change exactly 1 gram of ice into liquid water. We're going to set that equal to the information in our question. If we look back at this question, it doesn't tell us the amount of energy that we have. So that's going to be our unknown. I'm going to go ahead and put an X in there. But it does tell us that we had 100.0 grams of water. So we know the mass, and we can go ahead and plug that in. Once we get here, all we'd have to do is cross multiply to solve for x. If we do that, we should see that x equals 3,000, or sorry, it's going to be 33,000. Always good to double check yourself. Okay, cool. 33,400 joules of energy. And that is just going to be the amount of energy it takes for us to melt the ice. So that's just this first step. We can then move on to the second step. We would be looking at this region here. Oh boy, can I keep it consistent? I think we used pink in the first video. This region here, as we look, our temperature is increasing over time. So during this region, the temperature of our water is changing, which means we need to, again, identify which constant we want to use. During this part of the graph, our ice has melted. So we have just liquid water left. That means we want to use the specific heat capacity for liquid water. It tells us it's for liquid water, and we are talking about liquid water. So that's the one we want to use. So I'm going to abbreviate this by just saying heat capacity liquid, which is 4.184 joules of energy for every 1 gram and every 1 degree Celsius. So as we set up this calculation, I'm going to start off by saying it takes exactly 4.184 joules of energy to change 1 gram by 1 degree Celsius, but we do not know how much energy it's going to take for this step. What we do know is that we have 100.0 grams of water, and we know that I'm going to change the temperature from 0 up to 100. So the change in temperature is always our final temperature minus the initial temperature, which is going to get me 100 degrees Celsius. So even though in this instance my final temperature and my change in temperature are the same, that is not always going to be the case. And it's important for us to remember that it's the change in temperature, or the delta T, that we are plugging in to this side of our ratio. It is never just the final temperature, and it's never just the initial temperature. So then once we get here, we can cross multiply and solve for x. And what we would find here is that x equals 41,840 joules of energy. And that is the amount of energy that it takes for the second step. So then finally we get to our third step. I'm blanking on the colors that I used. I really like purple, so it's probably purple for this third step here. If we look at our graph once again, our temperature is staying the same because we are starting at 100 and ending at 100. That means that any extra energy is going into changing the state of matter, to breaking the attractions between those particles so that we can actually change phases. This higher phase change, this higher temperature plateau, is always going to represent vaporization, which I abbreviate VAP. So we are going to use the heat of vaporization for this last step, which is 2,260 joules to vaporize exactly 1 gram. If we look at that number and compare it to the others, hopefully that sticks out to you as significantly higher. So it takes a lot of energy to actually vaporize a liquid, because we have to break those particles free of all of their attractions so that they can fully separate from each other, and the substance can expand to fill its container. So if we look here, again, it takes 2,260 joules of energy to vaporize exactly 1 gram. On the other side of our proportion, we do not know how much energy we have, but we do know that we are vaporizing 100.0 grams. So again, we can set up our proportion. We've got our x. We just need to cross multiply to solve, and we'd see that x equals 226,000 joules of energy. So here we go. We've got step 1, step 2, and step 3, and we figured out the amount of energy in each of those steps. So the last thing that we need to do here is just go ahead and add those up. So if we do that real quick, we should get, it's like 301,240 joules of energy. The last question we want to ask ourselves when we're doing an energy calculation is if all of these Q's are positive or negative. So again, Q represents heat. In this instance, we are adding heat to the water. So each of these Q's is going to be a positive number, which means our final answer here would be positive 310,240. I guess the last step we could do here is kind of take a look at my sig figs. I guess those are a little bit off, and we should maybe end up with an answer that is 310,200 joules of energy. But either way, we're all right. The sig figs are not our main focus here on this question. So this is 3 separate problems where we identified which constant we need to use. We set up a proportion, and then we solved for our unknown. Then at the end, we added all of these energies up so we could see the total amount of energy that it takes for us to go ahead and fully vaporize or fully boil all of this water away. So hopefully watching me work through these questions has given you some help, made you feel a little bit more confident about these types of questions. But I'm going to end it here. And in another video, one of us will go over how to do some more calculations and eventually get into these 2 or multi-step calculations that we're going to see at the end of the unit. Thanks for watching. Have a day.